Hey everybody, thanks for coming. My name is Field Katie, and this webinar is called Python for Data Science. For those of you who might have seen the webinar when I gave it the first time and are noticing some differences between that and this, we had some technical difficulties in recording the webinar when I originally gave it, so I'm re-recording it now, and that's the cause of any differences that you might see. So the goal of this webinar is to give you an idea of how you can use the Python programming language for your own data science applications in the real world. Python is a language that is not data science specific, but it is very popular among data scientists and has a lot of great libraries and great tools for that kind of work. And to give you sort of a calibration, I'm assuming that you have what I call a hello world familiarity with Python. You've maybe read a tutorial or two, probably played around with some code, you know what a dictionary is and a list, but you haven't really seen the language in action on real problems. And my goal here is to move you from this hello world understanding to being able to apply this to your own data sets and get real cool insights. Now, before I go too much further, I want to back up for a sec. This talk is about Python in data science, not Python in general. Python is a general-purpose programming language. You can use it for data science or for production code. But those are really two different beasts in a lot of ways, although there is certainly overlap. In production code, typically you know more or less what you're creating. You can write out the functionality that it should have, and while you might go about it in an agile way and create an add-on functionality later, you can kind of have your eyes on the prize, and you are sort of curating a growing and improving code base. Data science is, you iterate a lot more quickly because you don't go into it generally knowing what the questions are that you're going to be asking. If you knew exactly the question to ask and exactly the analysis to do, then you probably didn't need to ask the question in the first place. There's a large exploratory component to data science. You start off with some business questions, get some data that's relevant, write some code that does some kind of analysis and maybe produces a scatter plot as the output. And once you get that output in hand, then and only then do you have an answer or a partial answer to the questions that you asked. At that point, you can refine the questions. You can realize that you asked completely the wrong question. You don't know until you get the graphic or other output in hand. And at that point, you have to change the analysis in ways that you didn't necessarily anticipate, rerun the code, and get your second round of results. It's this quick evolution rather than a growing, expanding code base with more functionality. And the goal of a lot of what I'm going to talk about in this webinar is to tighten this feedback loop, either by making it faster for your code to run. That's a very small concern, but I'll talk more about that in a second. The ability to change the code quickly is a big deal, as is the ability to interpret the output of your code. So to just delve a little bit more into the difference between production and data science code. In production code, you also are typically working with a much larger code base. It can be, hundreds to tens, possibly hundreds of thousands of lines of code that typically will run many, many times and will be run by people who had nothing to do with actually writing it. So you have to there's going to be a lot more time spent running it than writing it, so you have to worry a lot about is it efficient? And there's so many bells and whistles that get included that the name of the game becomes about creating bulletproof APIs that hide complexity, hide optimizations, and simplify the product down to the point where a human programmer can wrap their head around the piece of the code they're working on. In data science, Yeah, as I mentioned, you don't know what product you're creating going into it, which makes things more difficult. On the other hand, it's typically going to be a lot simpler. You generally have one or a handful of questions that you have to ask, and no one's going to make too big a deal about it if everything is not formatted perfectly and it has a gorgeous UX. That's a secondary concern. You're interested in just answering questions. It's usually being done for internal consumption. Most data scientists work for a company, and their results aren't going out to consumers. They're going to their boss or other data scientists, and there's a smaller audience. So there's a smaller code base generally that you're working with, small enough that it's reasonable for one data scientist to pretty much understand the whole thing, and be able to modify all of it. So the style focus between production and data science code is really kind of opposite. Production code is all about hiding complexity and hiding optimizations under these clear APIs. Data science is really about making all those things glaringly obvious so that when and if you need to change that part of the code in the process of iterating, you can go back to it, figure out how you did it the first time, change what needs to be changed, and rerun it. One thing that generally is not a big concern with data science code is performance, at least compared to production code. Production code, you worry about shaving off seconds and milliseconds. In data science, who cares? Most data science code is going to get run, once or twice. At worst, it'll be a batch job that runs overnight, and then an extra 10 minutes to run doesn't really matter. The one big exception to this is in scaling. If you are working with a 100 gigabyte data set, then you start to worry about if the code takes several more hours than it really needs to. That's not just a lack of optimization in the code. That starts to interfere with the ability to to iterate quickly. You don't want the data scientist just sitting there twiddling his or her thumbs while the code takes a lot longer to run than it should. And for really large data sets, where you start to push up against the limits of RAM, you can get into situations where it's not just a question of the computation taking longer than it should, it's a question of whether the computation even finishes. So in this talk, I'm going to ignore any O of 1 performance optimization, but I will talk about how to cope with large data sets in a way that scales. So the first part of this talk, I'm going to give an overview of the Python language. It'll be partially historical. This will be review for most people here. The next thing I'm going to do is I'm going to walk you through some example code that I put together, just showing off some of the stuff that I'm going to talk about in the talk. It's just a small data science example looking at Wikipedia page views, using them to compare operating systems, and I'll talk more about that a little bit later. The next section talks about tips for using the core Python language. And again, hello world familiarity. You probably have used lists and dictionaries, but you might not perhaps know what an iterator is or understand the ways in which it can be superior to a list. More about that later. And then the final section of this talk, I'm going to get into stuff that really is truly data science specific and look at some of the libraries that you use for Python data science, how they relate to each other, what's going on that makes them efficient, and some of the goodies that they contain. But that's for later. The Python overview. Python is a scripting language. It first came out in 1991 and was created by Guido van Rossum, I think I pronounced that wrong, but he was formerly at Google, and now works at Dropbox. It's if you've used Perl or Ruby or any of these scripting languages, it's very similar in a lot of ways. Although I, like many Python people, would argue that it has a much cleaner syntax than most scripting languages. Perl is a conspicuous example. The type system is pretty famous. It's dynamic typing. It's strongly typed, so it makes sure you aren't going to add an integer to a string, but it enforces all of these things at runtime, which makes the language slower but adds some flexibility. In terms of the programming paradigm, the language is more or less procedural, and it is object-oriented in very fundamental ways. Everything you ever create in Python is an object. But people who write Python code often try to make it, as functional as possible. But it's a multi-paradigm language. Now, the data science code example that I put together, what it does is it's trying to compare Mac OS to Linux to the Windows operating system. There's a lot of ways that you could compare these things, and the metric that I came up with was mostly just to make the data science code kind of interesting. Wikipedia has a category for each one of these operating systems of all articles that are related to that operating system. Linux pages might include awk and the article on Linux itself. What I use to compare these operating systems to each other is I pull down the page views to each of the articles that falls into their different categories. And then for each category, I look at what is the average traffic to articles in that category by a day of the week. So for example, I might say that articles in the Mac OS category tend to have 10,000 page views per day on Wednesdays. The way the code is architected is first I gather the data. That takes place in a shell script with Python used to do some parsing. The data is all stored it's all in the internet. You can access it through a public API, and I pull it down onto the computer and store it as JSON. The next step is I stream this JSON data through a Python script, once again, that will parse it out into a CSV file that you can feed into any number of different analysis tools. The calculation of the average traffic is not done in pure Python. Remember I talked about how scaling can be a big issue. One way to deal with scaling in very large data sets is to use Hadoop. Full disclosure, Think Big Analytics, my company, specializes in Hadoop. And so we're very big on Hadoop, and I'm going to use a Hadoop wrapper called Pig. And I will plug Python into it. But Pig is used to spread the computation across an entire cluster of computers. Native Python doesn't really do that. Then the final step in the code is I take the results of the Pig computation, put them back into a CSV file, and then plot that using some Python libraries. To show you what this code looks like itself, generally the way I write my data science code is I have a script called run.sh. It's a shell script, and it acts as sort of the glue that combines all the different parts of my code. This way, 3 months later, I can forget how any of this runs, just cd into that directory and say sh space run.sh and kick everything off. So within this shell script, I define some parameters at the top. There's a directory for my raw data, that'll be the JSON, a directory for intermediate data, and then a directory for the final output, which is that graphic that I showed you. I start by throwing out the directories if they exist, and then making them nice and brand spanking new. The first step is where I get the JSON down from the internet. I say for each one of the categories, remove the JSON file if it already exists. And then for each language, I look at Russian, Hindi, and Chinese. I think that the graphic that I showed you was actually just for the Chinese language. I curl down the Wikipedia page for that category. And I pipe it through this script called getCategoryFromPages.py. So I run the HTML for the category page through this script, and it identifies all of the different pages that fall into that category and spits them into standard out. And then for each one of those pages, I query this other API to get JSON describing the page views to that page and put it in a JSON file. So that would be macOS.json, would have a bunch of different lines of JSON for all the different pages that fit into the macOS category. Now let me just show you what that Python script looks like. I import sys, which is the way I access standard I/O. I define some functions, and then at the end, if name equals main, this is good Python practice for those of you who haven't seen it. It's a way to make it so that your script can be used either as a script or as a Python library. But I call this function that I called main. The main function, what it does is, while true, it just reads a line in the HTML that gets piped through it, and typically does nothing, because the first many lines in the HTML file don't contain any of the pages in the category. They're other boilerplate. But as soon as the string pages in category occurs in the HTML, that signals the start of the pages that will be present. So then we move on to this other while true loop. And for each line, if it starts with li in angle brackets, we call the getCatFromLine function and append its results to the list of categories. Then once this is all done, for each one of those categories, we just print it. Now the way I wrote this file is I downloaded the HTML files in question and looked at them in a text editor and made sure that the HTML was and figured out how the HTML was structured and wrote a simple parser for it. This is not using any of the HTML parsing libraries which exist in Python. This is very quick and dirty. So now back to the run.sh script. We've got our JSON files, our JSON data on the local machine. And what we do is for each category, we cat the JSON file through this file called parsejson.py and pipe it into a file like macOS_pageviews.csv. One little thing to note here is that I call parsejson.py with a command line argument telling it what category is being processed. The reason for that is I'm going to want this CSV file to have an extra column that says what the category is for the pages. It's going to be one row per category, but the JSON data that I downloaded does not contain in it, hey, this JSON was downloaded in reference to the macOS category. So I'm going to pass that in as a command line argument, and parsejson.py will add that as an extra column. So here's what parsejson.py looks like. Again, I have a function called main, and for each line in standard in, remember each line will be a chunk of JSON. Record is json.loadSLine. Record will be a dictionary containing all the parsed JSON data. The JSON data will contain the page views for multiple days. So for each date and views in the daily views field, I will create a list called toPrint that contains all the different columns, and then join that list into one line and print it to standard out. Note that the order of the output columns was defined at the top of the file here, and then referenced later. I also defined the delimiter at the top of the file. The next step is where I use pig to calculate the actual averages. The pig file looks like, the pig script looks like this. This isn't a webinar on pig, so I'm not going to talk a whole lot about it. Pig is conceptually pretty much just like SQL, except the syntax looks a little bit different. The one thing that is really interesting here is we define this weekday finder to be the shell command, Python datetoday.py, and telling it what column contains the date. What I'm doing here is the JSON data and the CSV data contains dates, 2012, 10, 13, whatever. But I'm trying to do this in terms of day of the week, and pig doesn't have a library to get the day of the week out, at least I don't think it does. So what I'm going to do is leverage a Python library to turn those dates into days of the week. The way pig is going to work is that each node in your cluster will have a subset of the data set, and each one of the nodes will kick off this Python script, then stream the data set through it, take the output from standard out from the script, and then have that be the next step in this process. But at the end what we get is just a table that says the language in question, the category like Mac OS or Windows, what day of the week, and the average number of views. Then we reformat that into one CSV file. Pig has some interesting ways that it structures its output. Don't worry too much about it. And then finally we call this analyze.py script on that output. Analyze.py is what's going to take that data set and actually produce the graphic that I showed you. Here's what analyze.py looks like. Note that I say up here what the order of the columns will be that come in. I have a main function that will read in the CSV file. It will assign it the columns. Then I tell it that the rows should be late in this data set should be labeled by the day column. I will break the output into a different data frame for Linux, for Microsoft, and for Mac. Then I'll combine them all, do a join, so that I'll have a row in the table that says Monday, and columns for Linux, Mac, and Windows. Then I will plot it as a bar chart and save the figure. So that's the data science project, and it creates the graphic that I showed you. And now back to the slides, but the slides will contain a lot of the tricks that I used in what I just showed you there. So without further ado, I'm going to move on to tips for the core Python language. Again, there's nothing data science specific here. These could be tips for any kind of Python programming, but they're ones that in my mind are especially useful for data science applications. The simplest one is just use a main function, like you saw me doing in my scripts. It's not strictly necessary for a language like Python, but it makes it very easy to have, say, two different two slightly different workflows, both described in the same file. I will often just copy my main function and rename the copy main1 in the same file. Change main1 and then call main1 rather than main at the end. It makes it easy to modify your workflows, and probably more importantly, for readability, it makes you condense all of the logic in your workflow down into one concise, understandable subroutine that calls other functions. The second tip is to learn to love dictionaries. If you have a hello world familiarity with Python, you're probably familiar with dictionaries. They're just a mapping from things like strings to values. In the code that I showed you, the JSON was parsed and returned as a dictionary. When I first learned Python, I was told that lists are the workhorse data structure. They're what you really do your work in. But what I have found as I have done more coding is that really I used less and less lists and more dictionaries, because in most cases, dictionaries are the natural way to think of data. They are conceptually just a way of storing key value pairs. Usually the keys are names, and the values can be anything. They can be lists, they can be numbers, they can be other Python objects. But a dictionary is a way to store those key value tuples. And if you see in the code that I've got here, you can use the dict function to create a tuple from it, to create a dictionary from a list of tuples. And then you can get back to the list of tuples by saying the dictionary.items. You can also do dictionary comprehensions, which are very similar to list comprehensions. Under the hood, Python dictionaries are generally implemented as hash tables, which means that you have O of 1 amortized time to look up and access data. It's very fast. They put a lot of work into this data structure to make sure that it is extremely efficient so that people like me don't have to worry about it. We can just use it. The next tip is really just a reiteration of the previous one. Dictionaries are awesome to the point where Python is generally really just a thin wrapper around dictionaries. The different Python interpreters are different. CPython is different from Jython and so on. But by and large, they are implemented as dictionaries under the hood. Or if not implemented as dictionaries, the code is copied over from dictionaries and modified. If you define a class, called foo, under the hood, that's going to be stored as a mapping from the names of the member functions in that class, member functions and member data, to what the actual functions and data are. If you import a module is really just a mapping from names of functions to the functions. Again, it's a dictionary. And even just like creating and modifying variables is done with a dictionary. If I just say a equals 5 at the command line, what that will do is all of my global variables are stored in a namespace, and the a comma 5 key value pair is added to that namespace. So Python is just syntactic sugar around dictionaries. So take a tip from Guido von Rossum and accept that dictionaries are awesome. The next tip is to use something called zipping. There's a very innocuous function in Python called zip. And what it does is it takes in two lists and matches off the elements to give you one list of tuples. What I'm showing you here is a very simple example of using zip. I'm about to get to a much more interesting one. But in my code where I take dates and turn them into days of the week, I had a data structure that took in the code for a day of the week and gave out the string that describes that. I wanted to map 0 to Monday, 1 to Tuesday, and so on. The problem with something like that is that it becomes annoying for a human to keep track of making sure that the digits all map correctly. It's not a huge deal with 7 days of the week, but you can imagine that in similar situations it becomes kind of not readable for humans. So what I did in my code is I wrote down Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday as a list. And, we're all humans who speak English, so it's easy to look at this and say, oh yeah, those are the days of the week. So my code to day of week data structure that I used was a dictionary that mapped those digits to the elements of this days of the week list. Range 7 will just be a list, 0, 1, 2, 3, 4, 5, 6. When I zip that up, I will have all the tuples that I want, feed it into the dict function, and I get out my needed dictionary. Now here's a much more interesting example of using zip. Or I should say, this is an example where somebody should have used zip and didn't. Let's say that you've got like a list of lists that you're iterating through. Maybe you read them in from a CSV file or something. And let's say for each line you want to do some kind of processing. Well, you can say, all right, for each line, the name is the 0th element and the age is the first element, and maybe there's some other elements, so I'll pull them all out in that way, and then do whatever processing I want. That's fine, but it is asking for trouble as soon as this starts to become complicated. What do you do if there's 50 columns? You have hard-coded into your code the locations of every piece of data. What if the column order changes on you? You might not know. This is horrible to maintain code, and I have seen it done by people in practice, and the code was sufficiently unreadable because there were like 50 columns in the data set that there was a really nasty bug that was hidden very subtly in the script that was not caught, and then it was discovered way later and turned into a firestorm. So doing this is asking for trouble. What should have been done is to define the columns in one place. And yeah, you have to define what the columns are, but just hard-code them in one place that's easy to modify. And then for each line in your data, zip the line up with the columns and feed it into a dictionary. Because ultimately you don't care about what order the columns are coming in for the most part. Conceptually, what you want is a mapping from the column headers to the elements in any individual line. Again, dictionaries are usually the natural way to think about your data and the problem that you're solving. Doing it this way also has the effect of separating out the details of the schema, from the core logic of what you're doing. My next tip is to master string manipulation. You might say, hey, that's a pretty standard tip, especially for a scripting language like Python. And yeah, it's very true, it is. But the reality of life in data science is that you have very weird data, and string manipulation can come to the rescue. And I wanted to make sure that I called that out. One of the most robust pieces of core Python is the string class. It has all kinds of cool things. Right here I'm showing you how you can split a string into a list of substrings and combine a list of substrings into one large string. Tricks like, if you work as a data scientist, a reality of life will be that you will spend a huge amount of time parsing through bizarrely, perversely formatted data. And the reason you're using a language like Python in many cases is you can't feed that data into R or SAS or anything like that. You have to deal with it in a little bit more of a raw form just because the formatting is so perverse. And in situations like this, string manipulation is what comes to the rescue. Here's some other simple examples. You can do string formatting. One of my favorites here is at the bottom where I say Jane is equal to template2, %, name goes to Jane, age goes to 39. That lets me substitute in those fields in multiple places in the string. This is an example of one of the big things I want to call out about strings and how they're useful in data science. Going back to the beginning of the talk where I was talking about the difference between production and data science code errs on the side of being quick and dirty. If the task at hand is something like parsing HTML, which I did in the code that I showed you, there's typically a right way to do it. I say right in quotes. That uses some fancy library that can do all kinds of cool, awesome things. And Python has those libraries. But if you're doing data science, you are often in a situation where it's really not that complicated, and it's probably not worth your time to go look up and master the correct library to use and then figure out how to use it. In many cases, you can just get by with string formatting. And that's what I did when I was parsing the HTML for the data science code that I showed you. The HTML was pretty simple, so I didn't have to worry about figuring out how to do it using the HTML parsing library. It saves my time, and it also saves the time of somebody else who might be reading my code. And true, this doesn't really scale. If you ever have to do very fancy HTML parsing, you'll have to learn the library. But in data science, you often never actually get to that point. So string formatting can do a quick and dirty solution to a lot of different problems. And here's a few more of my favorite built-in functions for strings in Python. I use ends with and starts with a lot. You can strip off white space. That's extremely useful. You can pad on new white space. You can check whether something's all digits. You can replace. There's all kinds of these built-ins. Learn them. They make life happy. Now the next tip is a little bit of a change of pace. Everything that I've been saying so far is aimed at making your code readable and comprehensible for humans. The next tip is moving to performance considerations. Again, we don't care about O of 1 performance hacks, but we do care about issues of scaling. And one of the biggest problems that you run into with scaling in Python is taking up memory. One of the big offenders is lists. Lists are great, they're awesome, but the problem with lists is that the whole thing gets stored in memory at once. And for a large data set, that will kill your RAM and make things a lot slower. So instead of using lists, you can often use iterators. An iterator behaves a lot like a list, except that you have to go through the elements one at a time. So if you want to add up everything in a list, or find the maximum thing in a list, you could use an iterator instead. It's all just one pass. If you want to bounce around between different elements, you'll have to use a list. But when an iterator is appropriate, the elements are created one at a time and stored. There's just an O of 1 memory fingerprint. And a lot of Python operates in iterators rather than actual lists by default. For example, sys.standardin is an iterator. It gives you the lines one at a time, so you never are hogging memory, even if you end up going through a lot of different lines. A slightly fancier tip for Python is if you like iterators, then you should start to think about the itertools library. It's a standard library for Python, and it contains all the cool things you could ever want to do with iterators. For example, I mentioned the zip function that takes in two lists and returns a list. Well, the itertools library has a function called izip that takes in two iterators and returns an iterator, giving the paired off elements of those two lists. So it's much more efficient if you're zipping two very large lists. If you want to iterate through all the different subsets of a list, you can do that and not have to worry about the exponential overhead of storing all the subsets at once. You can do group bys, you can do all kinds of cool stuff with itertools. And then my next slightly fancy tip is to use sets. For myself, I actually was using Python for a long time before I realized that the set data structure existed. And it's just a way to store unordered, unique collections of things. It's like a set in math. And an example of when you might want to use a set is, let's say you've got emails, from Bob to Jane, from Jane to Bob. You might want to be keeping track not of who the sender and receiver were, but of who the conversation was between. And using sets saves you the annoyance of trying to impose some artificial ordering on Jane and Bob. Again, this is getting back to what is the natural way to think of your data. And a lot of data truly is just collections. And if that's the natural way to think of it, then sets are the data structure you should be using. And those are my tips for the core Python language. Now I want to move into the stuff that really truly is data science specific. One of the great things about Python in general is that there's all kinds of libraries that exist for it. There's a lot of great libraries that are built into the language, and there's a lot of great libraries that are easy to install, that are free on the internet. And the libraries that are for technical computing, there's a lot of them, but here's on this slide some of the core ones. And they all play well together. They depend on each other in the way that I've illustrated here. The Numpy library is really sort of the core library. It creates arrays of numbers that you can manipulate very efficiently, store very efficiently. SciPy is a bunch of special purpose numerical computing tools like optimization and interpolation. I actually contributed to the interpolation code in SciPy. But a lot of stuff that operates on and rides on top of NumPy arrays. Matplotlib will plot and do graphics with these arrays. scikit-learn provides a lot of machine learning functionality that again rides on top of SciPy and NumPy. And pandas is similar to R, and it again relies on NumPy. And so these libraries all play well together. And the reason they play well together is that under the hood, most of them are based on NumPy arrays. So let's get a little bit more into the NumPy language. I'm not going to talk, the NumPy library. I'm not going to talk a whole lot about the syntax of it. I'm going to talk about what it is conceptually. When it comes to actual code, I'm going to show you the libraries that wrap NumPy. The core data structure in NumPy is just an array of numbers. It can be integers or doubles, and they are stored very compactly. You can do arithmetic operations in a very, very fast, vectorized way on them. And building up from that, you can do fancier mathematical operations like in SciPy. So here's what it looks like under the hood in terms of how memory is stored by the Python interpreter. If you have a normal list built into core Python, and say it's a list of numbers. It'll actually be a list of pointers to Python objects. And each one of these Python objects that is pointed to will have some metadata in it to denote that, hey, I am an integer, rather than a float, or a dictionary, or a module, or a string. And then on top of all that, in addition to all that overhead, you'll finally have, the number 3. So there's a lot of memory overhead in the way this is stored. And if you want to just add 1 to every element in this list, what you have to do is loop through the list of pointers. For each pointer, you go to the int type object that it points to. You figure out, okay, this actually is an integer, because in Python it could have been a string. You parse out the integer from that object, add 1 to it, create a new integer object, point the original pointer back to this new object, and then flag the original one for deallocation. There is a lot of overhead here. In contrast, under the hood, an array of integers in Numpy will just be stored as an array of integers. And the pseudocode for incrementing everything in this array by 1 is just for each index in the array, increment that element in the array. I ran a small test on my Mac and found that this was 15 times faster than the Python approach. And in fact, actually, it would be an even bigger win than that for large data sets. I was using, I think, 1 million elements in my list. But this is a much more compact way to store the data. So if you're using NumPy arrays instead of lists, you will start hitting cache misses a lot further down because everything can be compacted a lot more. So NumPy arrays are the way to deal with large sets of numbers in Python. Now I'd like to move on to the pandas library. The core data structure that pandas gives you is what's called a data frame. And you're probably familiar with data frames from R or tables in SQL. They're all conceptually more or less the same. You have a table with different rows, and then there are a certain number of named columns, each of which has a type associated with it. In what I'm showing you here, there's an age column that's an integer and a float and a weight column that's a float. The one thing that is kind of interesting about data frames in Python is that you also have what's called an index, which is sort of a name or a title that's given to each row in the data. So in this case, the index is a person's name, and then I give data about that person. It could be also an employee ID number, and then data about that employee. Pandas supports all the standard relational operations like joins and filters and so on. But under the hood, this age column will be stored as a NumPy array of integers. So it'll be very efficient to, say, add 1 or add 2 to all the ages, or to loop through and find the ages that are greater than 18. The weight column will also be stored as an array of floats with the same efficiency gains. This is the same way that R does it, if you're familiar with data frames in R. The index will be stored as an array of strings, which don't have the same computational wins as arrays of numbers, but you're typically not going to be doing any heavy processing on the index in the data frame. And here's some very simple pandas code. I import it. I typically call it PD myself. Pandas has a read CSV function that will read in a data frame as a CSV file and does a very good job of telling which columns should be integers and so on. You can instead start with a Numpy array and turn it into a data frame by imposing what the columns are going to be. And you can also create data frames from dictionaries. Here I've got a mapping from column names to lists giving the contents of that column. Here's the syntax for basic things like adding one to a column or selecting several different columns, filtering out the rows that don't meet some criterion, and you can also look at the rows by index. And you can do fancier things. All the basic relational operations fit into pandas. It's a very extensive library based on these data frames. I use it a lot. If you like what you see, then there's a lot of resources online. And pandas plays well with matplotlib. So what I'm doing here is producing several different plots of data. I can say just my data, open bracket, price, close bracket. That pulls out the price column, dot plot. That'll give me a line plot of the contents of that column. If I instead pull out two different columns, A and B, and do a plot, I will get two line plots. Or if I say kind equals bar, it'll be bar plots, like in the graphic that I generated with my example data science code. And then you can finally either display the figure and look at it and play around with it, or you can save it out for later inclusion into a report or whatever. And I think the final library that I want to talk about is called scikit-learn. And this is a data science talk. What kind of data science talk, if it's self-respecting, does not include some machine learning? Like all these libraries, scikit-learn is based on Numpy arrays under the hood, but it brings into play classifiers and regression and things like that. So here's some very simple code that uses scikit-learn. I import the datasets library from scikit-learn. It has a lot of built-in standard datasets. The digits dataset is a bunch of images that are handwritten digits. R does the same thing in that it has some famous datasets that are built in for putting together example code. I generate a support vector machine classifier, and then I tell the classifier to fit itself to my data, passing in the features and then the ways they should be classified. And then classifier.predict will create a vector. Will create an array of the predicted categories. There's a lot more in scikit-learn than this. It's a very extensive machine learning library, but that just gives you a little bit of a flavor for it. And then the final thing that I wanted to talk about was Hadoop. I mentioned Hadoop is a tool for scaling a computation across a large array of computers rather than just one single machine. It implements the MapReduce paradigm, which was popularized at Google. The downside of Hadoop is that there's a lot of Java. It's written in Java and it's designed for people who are very good at Java code. Personally, I'm allergic to Java. I write Python. I like flexible types and all that. So for people like me, Pig is a wrapper language around Hadoop. It's conceptually very similar to SQL if you're familiar with that. And under the hood, it compiles down into MapReduce jobs. Basically, a MapReduce job, what it does is you've got your data set that is spread across multiple nodes in the cluster. A single pass in the MapReduce we'll have each node do some processing on the subset of the data that it contains. And then there will be some output generated. And the output will potentially be of several different types coming from a mapper. And different types of output are routed to different what are called reducer processes. And each reducer process, which again will of course run on a node in the computer, a node in the cluster, aggregates all of the data of a particular type, and then the outputs of the reducers are the final result of the MapReduce job. So the map jobs are all done in parallel, the data routing can be done in parallel, the reducers run in parallel. MapReduce is great for scaling to large data sets. Now the way Python fits into this whole thing, and I talked briefly about this earlier, is on a given node, either a mapper or a reducer, its data is stored just as text files. And what it will do is it will kick off this shell process, Python calc_weekday.py, just like you might kick it off from the command line terminal. And then it will stream its data set into this script. And then the output of this script that gets written to standard out, Pig will then interpret as the outputted relation. So in this case, I streamed in data with two columns, dates and page views, and I get out two columns, day of the week and page views. Here is the code that I showed you in the walkthrough. When I say define weekday finder as Python calc_weekday.py, the command in tick marks there is the shell command that gets run. And then when I say ship calc_weekday.py, that means that this Python script will get copied over to all the different nodes in the cluster so that each of them can use it to operate on their subset of the data. Is there overhead involved in this? Yes, there's actually quite a bit. Besides the fact that Python is slower than Java, certainly, there's a lot of overhead involved in accessing standard in and standard out. But this is a data science situation where typically the time for a developer is a lot more valuable than the time for a computer. What often will happen is you perfect the process using streaming like this. At least that's what I do. And then when I get it to the point where I know what has to be done, if performance is an issue, which it often isn't, but if performance is a big issue, then we can replace this Pig script with some custom JavaScript. Pig and Hadoop are great at plugging in custom JavaScripts. Here's what the Python code looks like. Again, I showed it to you when I walked you through it. You import sys so that you can access standard in and standard out. And for every line in standard in, you strip off the white space and split the line into the different columns. And I should have said dot split there, so this code wouldn't actually run. Then you produce the output columns. You join them with tabs into one line. Pig streaming interprets tabs as the separator between columns, and then print the output. And a nice sort of happy medium in a lot of cases between writing, between Python streaming that incurs the overhead and writing hardcore, hands dirty Java code is to use the Jython interpreter. It's a Python interpreter that's written in Java and runs on the JVM. So you can write Python code like this, but it gets compiled into a jar file that can run much more efficiently in Pig than raw Python. Instead of Pig, if you wanted, you could have used the Dumbo library, which lets you create your mapper and reducer functions just in pure Python. So you're being explicit about what things are maps and reduces, but you are never actually writing code in a language besides Python. And then finally, if you don't like Dumbo, PyDup is another very similar library where your mappers and reducers are defined as classes rather than just as functions. And that is my talk. Thank you so much for your time.